1. Introduction to the Falling into Earth simulation. The Falling into Earth simulation is a physics model that investigates what would happen if a person or object were able to fall through a tunnel passing through the Earth. Imagine a very long straight tunnel that starts at one point on Earth's surface, goes through the center of Earth, and comes out at the opposite side. When the object is released, Earth's gravity pulls it toward the center. The simulation allows us to observe how the object's position, velocity, acceleration, and energy change during the journey. This is mainly a theoretical experiment because it is impossible to create such a tunnel in the real Earth. The temperature and pressure inside Earth are extremely high, and Earth's interior is made of different layers and materials. The simulation is useful because it helps students understand gravitational motion in a situation that is difficult to observe directly. Gravity at the Earth's surface. When the object is released at the Earth's surface, gravity immediately begins pulling it toward Earth's center. Near Earth's surface, gravitational acceleration is approximately g equals 9.8 meters per second squared. This means that, if we ignore air resistance, the object's velocity increases by about 9.8 meters per second every second during the initial part of its fall. For example, at the beginning, velocity equals 0 meters per second. After 1 second, velocity approximately 9.8 meters per second. After 2 seconds, velocity approximately 19.6 meters per second. After 3 seconds, velocity approximately 29.4 meters per second. However, this simple calculation cannot be used throughout the entire journey because the object moves inside Earth. At the beginning, the object has a large amount of gravitational potential energy. As it falls, this potential energy is converted into kinetic energy, which causes its speed to increase. What happens at the center of Earth? The center of Earth is a very special point in the simulation. At the center, gravity from the surrounding Earth acts in all directions. These gravitational pulls balance each other, so the net gravitational force is 0. Therefore, gravitational acceleration at the center equals 0. But this does not mean that the object suddenly stops. The object has already gained a large velocity while falling toward the center. Because of inertia, it continues moving through the center. In fact, in the idealized model, the object's speed is greatest at the center of Earth. This is similar to throwing a ball upward. The ball continues moving even when the acceleration changes its motion. In the Earth tunnel, gravity causes the object to slow down only after it has passed the center. How gravity decreases inside Earth. One of the most important ideas in the simulation is that gravity does not stay at 9.8 meters per second squared throughout the entire Earth. As the object moves toward the center, the effective gravitational force becomes smaller. In the simplest model, Earth is assumed to have a uniform density. Under this assumption, the gravitational acceleration inside Earth is approximately proportional to the distance from Earth's center. So, at the surface, gravity is strongest. Halfway toward the center, gravity is weaker. Close to the center, gravity is very small. At the center, net gravity is 0. We can represent this simplified relationship as g of r is approximately equal to g0 times r over r, where g of r is the gravitational acceleration at distance r from the center. g0 is the gravitational acceleration at Earth's surface. R is the distance from Earth's center. R is Earth's radius. This explains why the object does not continue accelerating at 9.8 meters per second squared all the way to the center. 5. Maximum speed of the object. The object reaches its maximum speed at the center of Earth in the idealized simulation. Why? While the object is above the center, gravity pulls it toward the center, so its velocity increases. As it gets closer to the center, gravity becomes weaker, so its acceleration decreases. At the exact center, acceleration is 0. However, the object has accumulated kinetic energy during its fall. Consequently, it passes through the center at its highest speed. After crossing the center, gravity begins acting against the direction of the object's movement. The object therefore starts slowing down. In the simplest uniform Earth model, the maximum speed is around 7.9 kilometers per second for a fall from the surface through a diameter, although the exact value depends on the assumptions of the simulation. Motion after passing through the center. After the object passes Earth's center, something interesting happens. Suppose the object is traveling from the North Pole toward the South Pole. Before reaching the center, gravity pulls it toward the center. After passing the center, gravity still pulls it toward the center, but now the center is behind the object. Therefore, gravity acts opposite to the object's velocity. The result is deceleration. The object's speed gradually decreases as it moves toward the opposite surface. Eventually, velocity equals zero at the opposite surface. If there were no energy losses, gravity would then pull the object back toward the center again. This means the object would continue moving back and forth through Earth. Simple harmonic motion. The falling into Earth simulation is closely connected to simple harmonic motion. In the ideal uniform density model, the gravitational force inside Earth is proportional to the distance from the center. F is strong R. The negative sign means that the force always points toward the center. This is mathematically similar to the force produced by a spring. F equals negative kx. Because of this relationship, the object's motion resembles the motion of a mass attached to a spring. The object would start at one surface, accelerate toward the center, reach maximum speed at the center, slow down after passing the center, stop momentarily at the opposite surface, fall back toward the center. Repeat the process. If there were no friction or air resistance, this motion could theoretically continue forever. Real-world limitations and conclusion. Although the simulation is very useful, it is based on several assumptions that are not realistic. Extreme temperature. Earth's interior is extremely hot. Materials inside Earth would behave very differently from ordinary materials near the surface. Extreme pressure. Pressure increases enormously as we move deeper into Earth. A tunnel would not remain stable under these conditions. Earth's different layers. Earth is not made of material with uniform density. It has the crust, mantle, outer core, and inner core, each with different properties and densities. Air resistance. If the tunnel contained air, the falling object would experience drag. This would remove mechanical energy and change its motion. Earth's rotation. Because Earth rotates, an object falling through a tunnel would be affected by rotational effects, including the Coriolis effect. The object would not necessarily travel perfectly along the tunnel's center line. Friction. Friction with the tunnel walls could also remove energy from the system. Therefore, the real motion would be different from the ideal simulation. Overall conclusion. The falling into Earth simulation is an excellent example of how gravity changes inside a planet. It demonstrates that an object does not simply accelerate at a constant rate all the way through Earth. Instead, its acceleration decreases as it approaches the center. Its speed reaches a maximum at the center, and then it slows down as it travels toward the opposite surface. The simulation connects several important physics concepts: gravity, acceleration, velocity, kinetic energy, potential energy, inertia, simple harmonic motion. So the main lesson is that gravity always pulls the object toward Earth's center, and this creates an oscillating motion in the idealized model.